Okay, so in the event that you missed a class that went over electric circuits, we're going to go ahead and just do a quick video recording for you. So this is part 3 of the unit on electricity, magnetism, and universal law of gravity. So we're going to start looking at electric circuits. Any path along which charges, usually they're electrons. Remember, the electrons are the things that are loosely held to the parent nucleus, and so they're the ones that are charge carriers for electricity. So any path along which charges can flow between the terminals of the voltage source. That voltage source could be a battery, it could be a generator, anything that's going to be able to provide a potential difference to drive those charges. You need to have a complete circuit in order for electrons to actually flow through there. So it's got to be continuous flow with no openings, no gaps. We'll often use a mechanical analysis or mechanical analogy to understand electrical current flow, simply because most students, or most people in general, are more familiar with the mechanical side of things than they would be the electrical side. So a pump is like a pressure source for a mechanical system. The equivalent for the electrical would be a battery or a generator. I'm going to show you what that would look like using the schematic over here for us. So if I'm going to draw a battery, it looks something like this. The small size, the large size there represents different cells within that battery. And so that would be a symbol for an electric battery. If I were going to use a alternating current source, it might look something like this, where you have a motor, could be a generator of some sort, that would look something like so. So typically they would draw just something that looks like a mechanical generator that could provide an alternating current source versus a direct current source. Okay? And so that would be the equivalent for the mechanical system, just for the electrical. Now, a valve in our mechanical systems, you open or close that to be able to allow the water to flow. A switch in an electrical system would look something like this. Typically has two terminals there, and then you have a gate or a bar that can open or close. Now, in contrast to a mechanical system, a closed valve shuts things off. An open valve allows things to flow. Well, that's opposite over here. A closed switch means that that is on. And an open switch means off. Okay, so again, they sort of they act opposite to each other. We need to have a complete circuit in order for us to allow electricity to flow. So we have to close that switch in order for the electricity to flow. And then a convoluted line in a pressure system would look something like that. That's actually very similar to how an resistor would look like when we go to draw that for an electrical circuit. It would look something like so. Okay. So again, we need to have a complete path for charges to flow, and then the basic circuit here looks very similar to what you'd have for a mechanical circuit. Now, we're going to look at two different kinds of circuits. One is a series arrangement, the other one is a parallel arrangement. Today's just going to be on series. If you are having to watch this video without having been in class, I did show a 9-minute video on visualization of current flowing through a circuit. But that won't work for this particular video here. So perhaps you can see that on a different with a different link. Series circuit. It's a single pathway for current. If one device fails, everything's going to shut off. And you can see that the battery source, the voltage source here, is going to allow the electrons to flow through that light bulb, through that filament, and then through that filament. So everything flows. All the current flows through each of those light bulbs. If one of those things breaks or the filament burns out, then the entire thing shuts down. Total resistance is the sum of the individual resistances. And I want to write that as an equation for you. And so if I want to get the equivalent resistance of the entire circuit, that would be the sum of the individual resistors. And you could have any number of these added in series. Now, that equation is a direct consequence of this equation. You might recall that resistance was equal to resistivity times L over A. Well, as I increase the number of filaments that might be connected in series, you can see that effectively increases the length of the path that the charges have to be able to flow through. So that's essentially increasing the numerator of that equation. The current in the current is equal to the voltage source divided by the total resistance. So if I want to find the current flowing through that battery, so let's say I have some electrical current flowing through there, that current can be found as the voltage from the battery divided by the total resistance. And again, that goes back to that I is equal to V over R concept that we studied in part 2 of this unit. Same idea here. Total voltage is divided across the individual devices, and the sum of all those voltage drops would be equal to the supply. So if this battery is let's say it's a 6-volt battery, and I have 3 light bulbs connected in series, and all of those have the same resistance, if you will, then each of these would get a 2-volt drop across that. And so if that were a 6-volt potential, that would be down to 4 volts, that would be down to 2 volts, and that would be down to 0. And of course, then that battery is going to be able to lift that potential back up to 6 volts. Now, the voltage drop across each device is proportional to its resistance. And so the idea behind that is that since all of these things have the same current flowing through them, then the overall voltage drop, delta V, would be equal to I going through that current, or through that circuit, multiplied by its resistance. So we can see that the larger the resistance, the larger the voltage drop. And so we can say that they are in direct proportion to each other. Now, the remaining portion of this video is just going to show you how to analyze something like this. We have 2 circuits. Both of them are just showing a simple series circuit, and I'm going to go through and just I'll show you how to determine the equivalent resistance and the total voltage drop across each device. It turns out that in your copy, not all the words were listed there, so you're going to determine again the equivalent resistance, total current, and the voltage drop across each device. Let's first go ahead and find Req. Since this is a series circuit, it would just be the sum of these 2 here, or sum of these 3, which would be 50 plus 100 plus 150, which would be 300 ohms. So that would be equivalent to a single resistor of 300 ohms of resistance. If I want to find the current flowing through through those resistors, it would be the voltage from the battery divided by Req. In this case, I have an 18-volt battery, and that 18 volts is going to be used to drive that current through 300 ohms of resistance. And when you go through and do that math, you get something that looks like that. So the 0.060 amperes, you might think of that as 60 milliamps. So again, each one of those, either one of those would be acceptable. Typically, we would use the 0.060 amperes when we're starting to determine things like voltage drop. If I want to determine delta V1, that would be the voltage drop across this resistor. So if I were to take a voltmeter and place it across here with maybe a red electrode and a black electrode connected to a VOM meter, like so, that would read for us the voltage drop across that particular thing. And so I take I, the current flowing through that device, multiplied by R1. That I is 0.060 amperes. Multiply that by the resistance of 50 ohms. And that turns out to be 3 volts of potential across that resistor. If this is at 18 volts, this is at 18 volts, this would be down to a 15 volt value. So I have a delta V across that resistor of 3 volts. Let's go ahead and determine the voltage drop across the second resistor. Same amount of current flowing through it, but it's got twice the resistance, so it should get twice the voltage drop across that. And so that would be reading about 6 volts across R2. That would put this potential, if that's at 15, that would put this one at 9 volts. Okay? And then finally, delta V3 would be the voltage drop across that. It should be 9 volts because if the battery is providing 18 volts of potential, then all of that is going to be dropped across these three resistors. That last one should take the remaining of that. Just go ahead and just check that. And sure enough, 0.060 multiplied by 150 ohms. Do that math, and you see that that's 9 volts. And sure enough, when I add those together, I get the 18 volts, which is what I was expecting. Okay, and then the last one we're looking at, if you were in class to do this, I would have had the students do this one by themselves. And so I would encourage you, if you're having to watch this video remotely, to try this one and see if you come up with the same solution as I have. Okay. So I'm going to go ahead and write this without talking. So in the event that you're trying to solve this problem on your own, you won't be listening to me do it. You can just see the video as you progress through it. And so again, no talking on that one, but hopefully you went through and were able to solve that problem on your own. Again, just pay attention to the kilo ohm being a kilo means 1,000. And so when I go through to do these things, I would convert that 18 kilo ohms to 18,000 ohms, so that when I go through to determine the current and take that 9 volts divided by 18,000, I get 0.00050 amperes. That would be equivalent to, let's see, 1, 2, 3, 4, 5, 6. That would be 500 microamps. And so micro means 10 to the negative 6, and so we might write it this way as well. When I go through to determine delta V's across that, you get 1.55 volts. 2.5, add them all together, you get 9 volts. This is what we should expect. And that completes this video on series circuit analysis. Good luck.